When we hear the words black hole, most of us imagine a cosmic monster far away, a place where even light cannot escape, entirely removed from the familiar rhythms of everyday space. But what if the story does not end there? What if black holes are not the strangest objects the universe has to offer? And more importantly, what if they are not as distant as we usually assume? Could some of them be present within the solar system itself, drifting silently through regions we believe we already understand? How many black holes might be moving between planetary orbits, emitting no light, no signal, leaving behind only the faintest traces as tiny deviations in motion? How could we ever know they are there, when no telescope can see them directly? If this question gives you pause, you are invited to share your thoughts. Leave a comment, like, share, and subscribe, and continue the conversation with us. For now, allow yourself to slow down and step gently into a journey of listening to the quietest movements of the universe. We open with a wide picture of the universe's unseen ingredients, from black holes and exotic stars to dark matter and dark energy, all appearing as quiet whispers that physics has been learning how to hear. There are times when the universe seems almost empty. We look up and see scattered stars, a pale band of the Milky Way, perhaps a bright planet drifting across the sky, and it feels as if most of reality is already on display. Yet when we listen more carefully, through long calculations and instruments that patiently watch the heavens, another picture begins to appear. A picture in which the most decisive parts of the cosmos are almost entirely invisible, present mainly as quiet influences and subtle shifts that unfold over many years. Long before anyone had a telescope powerful enough to see the neighborhood of a black hole, the idea of such an object existed only on paper. In the late 18th century, John Michel worked within the framework of Newtonian gravity and imagined a star so compact that its escape velocity would exceed the speed of light. In his calculations, light behaved almost like tiny projectiles, and gravity could, in principle, hold those projectiles forever. It was an abstract construction, a thought experiment nested inside equations, with no hope of direct observation at the time. More than a century later, after Einstein wrote down the field equations of general relativity, Karl Schwarzschild found a solution that described an even more striking object. Instead of a very dense star in the Newtonian sense, his result pointed toward a region of space-time where geometry itself curved so deeply that nothing, not even light, could climb back out once it crossed a certain boundary. This boundary would later be called the event horizon. Again, the whole structure lived first as a mathematical possibility, a consequence of a new theory of gravity, not as something anyone had actually seen. For decades, these objects were treated with caution. Some physicists regarded them as curiosities at the edge of the equations, perhaps signals that the theory was being pushed beyond where it should be trusted. Others took them more seriously, but still lacked any observational way to confirm that such extreme regions of space-time existed in the real universe. The gap between equation and sky stretched across generations of scientists, and the idea of a black hole hovered in that space between suspicion and acceptance. Then, in the early 1972s, observations of a bright X-ray source called Cygnus X1 began to change the conversation. Careful measurements showed that the X-rays seemed to come from materials spiraling in toward an unseen companion, an object with a mass comparable to a star but no visible surface. The simplest explanation was that this companion was a stellar mass black hole. What had once been a theoretical construct became, for many researchers, a concrete astrophysical object. The universe had not changed in that moment, but our willingness to let the equations describe something real had shifted. We do not need to resolve every detail of that story tonight. It is enough to notice that something can be entirely real and yet spend a long time existing only in the language of theory before we recognize its presence in the sky. The history of black holes offers a pattern that appears again and again in modern cosmology. As our measurements expand, we discover that the parts of the universe we can see directly are not necessarily the parts that carry most of the mass or energy. When astronomers reconstruct the overall budget of the cosmos, they find that ordinary matter, the kind that forms stars, planets, clouds of gas, and our own bodies, accounts for only a small fraction of the total. Roughly 5% of the cosmic energy density comes from this familiar material. The rest appears in two components that do not emit or absorb light in the usual way. Dark matter contributes around 27%. It clusters around galaxies and within galaxy clusters, shaping the way stars orbit and how these large structures hold together over billions of years. Dark energy makes up the remaining 68%, acting as a uniform energy density associated with the fabric of space itself, driving the accelerated expansion of the universe on the largest scales. Together, these invisible components dominate the cosmic ledger, even though they do not announce themselves through direct flashes of light. If we imagine the universe as a vast ocean, the bright stars and glowing nebulae are like a thin layer of foam on the surface. They are what we notice first, what we photograph and name. But the bulk of the mass and energy lies beneath, carried by something we cannot see directly. Our instruments detect the way galaxies rotate and how clusters bend the paths of light from even more distant sources. Our measurements of distant supernovae reveal that the expansion of space is speeding up rather than slowing down. These observations point again and again toward invisible influences that outweigh the luminous parts. Most of what exists does not ask to be seen. It reveals itself through the quiet way it steers motion and shapes the large-scale story of the cosmos. Within this invisible sector, dark matter and dark energy play very different roles, even though they share a name. Dark matter behaves like an unseen population of mass-bearing particles or objects. It gathers in halos around galaxies and helps bind them together, adding to the gravitational pull without contributing to the visible light. Astronomers inferred its presence when they noticed that galaxies were rotating too quickly at their outskirts for the visible matter alone to hold the stars in place. Additional mass had to be there, extending far beyond the regions where starlight fades. Dark energy, by contrast, acts not as a clustering substance, but as a property of space itself. When researchers measured the brightness of distant type Ia supernovae stellar explosions that can serve as standard candles, they found that the expansion of the universe was not merely continuing but accelerating. The simplest way to describe this acceleration within general relativity is to include a small, positive cosmological constant in Einstein's equations corresponding to a tiny energy density permeating all of space with an effective negative pressure. Rather than pulling structures together, this component stretches space apart more and more over time. In broad terms, dark matter adds invisible weight to galaxies and clusters, while dark energy changes how the entire cosmic fabric expands. They are two distinct kinds of invisibility. One gathers, the other spreads. Neither can be seen directly with a telescope, yet both shape the way the universe looks and evolves on different scales. For tonight, it is enough to recognize that our picture of the cosmos rests on at least these two unseen foundations, each inferred not from direct images, but from patterns in motion and light. The question, then, is how physics learns to listen to what cannot be watched in the usual way. Over the last century, the tools of observation have expanded far beyond simple imaging. We now follow the orbits of planets and moons with extraordinary precision, tracking how their positions shift over years and decades. We monitor the timing of pulsars and the distances to spacecraft as they navigate the outer regions of the solar system. We measure how the shapes of galaxies are distorted by gravitational lensing as light from more distant sources bends around clusters of mass. In this wider sense, the universe becomes not only something we look at, but something we listen to through many different channels. Equations predict how a planet should move under the influence of known masses. If its orbit shows a tiny, consistent deviation from that prediction, we treat that deviation as a kind of whisper, a clue that something else might be present. The same is true for the way galaxies rotate, for the exact pattern of temperature variations in the cosmic microwave background, and for the signal of gravitational waves passing through detectors on Earth. Our own solar system becomes part of this listening network. As Earth and Mars move around the Sun, their positions trace out a shifting geometry that can be modeled with exquisite care. Spacecraft orbiting Mars send back timing signals and distance measurements that tie the two worlds together in a web of data. In principle, if a compact object such as a small black hole were to pass through the outskirts of the system, its gravitational pull would leave a minute imprint on these trajectories. The change would be extremely small, spread over long intervals of time, and hidden within many other effects, yet still present as a possible signature. In the same way, the mathematics of general relativity and quantum field theory outlines other possibilities that have not yet been confirmed directly. Exotic stars with unusual forms of pressure, vacuum-like interiors that resemble dark energy, and mirror images of black holes called white holes all emerge as allowed configurations under certain conditions. These constructs begin as shapes in a diagram, as solutions to an equation, and then wait to see whether observation will eventually find something that behaves in a similar way. We do not need to decide, here, which of these possibilities will turn out to exist in the sky. The important shift is that our attention moves from demanding clear pictures to learning how to interpret traces. Subtle changes in motion, faint patterns in background radiation, quiet ripples in space-time, and long-term drifts in carefully predicted paths. Little by little, as we follow these traces, the invisible parts of the universe take on form. They do not step into the light in the usual sense. Yet they begin to occupy our mental map of reality as firmly as stars and galaxies. In the background, beyond the bright points we see with our eyes, an entire landscape of unseen structures and energies waits within the equations, hinting that there is more to the cosmos than its visible surface and inviting us to keep listening as the story continues. We begin here with the familiar light of ordinary stars, because understanding how they quietly hold themselves together gives us a reference point before we move toward more exotic, invisible structures. When we think about the sun, it is easy to picture a solid ball in the sky, a glowing disk with a surface that might feel firm if we could somehow approach it. In reality, the sun is not solid at all. It is a sphere of hot plasma, a sea of charged particles and radiation bound together by gravity. Every part of it is engaged in a long, patient balance between being pulled inward and being pushed outward. Deep in the core, where densities and temperatures are highest, hydrogen nuclei move so quickly that they can fuse into helium. In these fusion reactions, a small fraction of mass becomes energy, carried away in the form of photons and neutrinos. The photons begin their journey outward, but they do not stream directly to the surface. Instead, they scatter again and again off particles in the plasma. Each scattering changes their direction, and the path they trace becomes something like a long, random walk. Because of all these interactions, a single photon can take hundreds of thousands of years to work its way from the core to the visible surface. On its way, its energy contributes to the pressure inside the star. This radiation pressure, combined with the pressure of the hot gas itself, pushes outward against gravity. The result is what physicists call hydrostatic equilibrium. At each layer inside the sun, the inward pull of gravity is balanced by the outward push of pressure. We can imagine the star as a series of nested shells. In each shell, the weight of everything above presses inward, and the material within that shell responds by pushing outward. If gravity were to win, the star would contract. If pressure were too strong, it would expand. Instead, for most of its life, the star settles into a state where these tendencies match. The sun has been in such a state for billions of years, converting hydrogen to helium in the core, allowing its brightness and size to remain remarkably stable on human timescales. This balance between gravity and fusion-driven pressure is our first standard model of a star. It is the baseline against which we will compare more extreme states of matter and more unusual forms of pressure. However, the fuel that supports this balance does not last forever. In the distant future, when the sun has consumed most of the hydrogen in its core, the fusion reactions that maintain its present equilibrium will slow and rearrange. The core will contract and heat further, and the outer layers will expand and cool, transforming the sun into a red giant. Material from the outer regions will eventually drift away into space, leaving behind a dense core that no longer burns nuclear fuel. What remains after this transformation is a white dwarf. This remnant is roughly the size of a planet, but contains a mass comparable to that of the Sunday. Its interior is no longer supported by the pressure of hot gas and ongoing fusion. Instead, it is held up by a different kind of pressure that arises from quantum mechanics. In a white dwarf, the atoms are compressed so tightly that electrons are forced into states where they cannot be packed any closer without violating the Pauli exclusion principle, a rule that prevents identical fermions from occupying the same quantum state. The resistance to further compression from this principle is called electron degeneracy pressure. It does not depend on temperature in the same way as ordinary gas pressure does. Even if the remnant cools, this quantum pressure persists, providing a firm counterweight to gravity up to a certain mass. This change in support mechanism is a key step in our story. The star has exhausted the nuclear reactions that once pushed back against its own gravitational pull. Yet matter finds another way to resist collapse. The white dwarf shows us that there are forms of pressure not tied to heat and fusion, and that these quantum effects can shape the fate of stars. There is, however, a limit to what electron degeneracy pressure can sustain. In the 1930 seconds, Subramanian Chandrasekhar calculated that a white dwarf cannot remain stable if its mass exceeds about 1.4 times the mass of the Sunday. Beyond that threshold, the electrons cannot provide enough quantum pressure to balance gravity. This value, known as the Chandrasekhar limit, marks a boundary in the space of possible stellar remnants. If the core of a collapsing star is more massive than this limit, the evolution continues past the white dwarf stage. Under such intense compression, electrons and protons can combine to form neutrons, releasing neutrinos and transforming the composition of the matter. The density approaches that of atomic nuclei, and the remnant becomes a neutron star. A neutron star is a compact sphere only a few tens of kilometers across, yet it can carry more mass than the Sunday. In this environment, neutrons themselves provide the degeneracy pressure, resisting further compression through the same quantum principle that protected the white dwarf, but now applied to a different particle. The result is an object with immense surface gravity and a strong gravitational field, but still a distinct surface and a stable configuration, at least within certain mass ranges. We can think of the evolution from ordinary star to white dwarf to neutron star as moving along a sequence of support mechanisms. First, thermal and radiation pressure from fusion hold gravity in check. When fuel runs low and fusion subsides, electron degeneracy takes over in lower mass remnants. For higher masses, neutron degeneracy becomes the relevant form of resistance. Each step reveals another layer of how matter organizes itself under compression. Just as with white dwarfs, there appears to be a maximum mass for neutron stars. Detailed models that incorporate the Tolman-Oppenheimer-Volkoff equation, a general relativistic version of hydrostatic equilibrium for very compact objects, suggest that stable neutron stars cannot typically exceed about 2 to a little over 2 times the mass of the Sunday. The exact value depends on the equation of state, the relationship between pressure and density in this ultra-dense matter, which is still an active area of research. Observations of particularly heavy neutron stars help narrow down the possibilities. When a collapsing stellar core exceeds this neutron star mass range, even neutron degeneracy pressure is not sufficient to counteract gravity. At that point, according to our current understanding, the matter continues to collapse, and a black hole forms. The surface disappears behind an event horizon, and the remnant becomes an object described not by the properties of its material interior in the usual sense, but by its mass, spin, and electric charge as encoded in the geometry of space-time. The important theme, for us, is that ordinary matter has boundaries in how strongly it can push back. Each form of pressure can only support a star up to a particular mass before it yields. Hydrostatic equilibrium supported by fusion breaks down when fuel runs out. Electron degeneracy carries white dwarfs only up to the Chandrasekhar limit. Neutron degeneracy stabilizes neutron stars only within its own upper mass range. Beyond these thresholds, something more extreme must occur. By following this progression carefully, we prepare ourselves to consider states of matter and configurations of spacetime that go beyond the familiar sequence. The concept of a gravastar, for example, involves an interior region dominated by something that behaves like vacuum energy. With positive energy density and effective negative pressure, a configuration that can mimic a black hole from the outside while being structured differently within. Hypothetical exotic stars replace ordinary nuclear matter with more unusual components, such as deconfined quarks or other high-density phases. These ideas extend the pattern we have already seen. As gravity presses harder, new forms of pressure and new phases of matter become relevant. Each phase obeys its own limits. Somewhere beyond the neutron star boundary, the classical picture gives way to objects that are either true black holes or something very close to them, perhaps decorated with additional structure predicted by certain theories. For now, it is enough that we have established a clear baseline. We have walked from the sun's long-lived fusion balance to the compact stability of white dwarfs and neutron stars, guided by gravity's inward pull and the various ways matter resists compression. In the background, general relativity frames all of this as a story of curved space-time and pressure, contributing to that curvature along with mass and energy. From here, as we continue, we will let this sequence of balances and limits accompany us. It will serve as a quiet reference while we turn our attention to objects that may not yet be confirmed in the sky, but which emerge naturally when we follow the same lines of reasoning into more unusual territory. Now, we move into models of unusual stars, where pressure and energy density take on unfamiliar values and lead us toward the idea of gravastars connected to vacuum energy. Up to now, we have pictured stars held in place by familiar forms of pressure, supported first by fusion and then, in remnants, by quantum effects in ordinary matter. Gravity pulls inward, pressure pushes outward, and there is a balance that can last for a very long time. Now we imagine what happens when matter is pushed much further toward the edge of what these usual forms of pressure can do, and we ask how close a real star can come to the compactness of a black hole. A useful way to approach this is to think about gradually compressing an idealized star. We begin with a sphere of matter that has positive energy density and positive pressure everywhere, properties that match our intuition about normal material. It weighs something, and it pushes back when squeezed. Under its own gravity, such a sphere settles into a configuration where pressure rises toward the center, because the layers above press down. If we increase the central density, the gravitational pull strengthens, and the star becomes more compact. In 1959, Hans Buchdahl analyzed this situation within general relativity and found a surprising limit. For any static, spherically symmetric object made of matter with positive density and positive pressure, there is a minimum radius beyond which such an object cannot be compressed without violating the assumptions of the model. That minimum radius is slightly larger than the Schwarzschild radius associated with the same mass, the radius that would define the event horizon of a black hole. We can imagine this as a kind of safety margin that ordinary matter cannot cross while still behaving in a conventional way. As we compress the star, its radius can approach the black hole radius, but not match it. To go further, something in our description has to change. Either the object ceases to be a static star and collapses into a black hole, or we must let go of the requirement that pressure and density remain positive in the usual sense. The Buchdahl limit therefore marks a boundary between what we might call a realistic star made of standard material and the region of parameter space occupied by black holes. It also suggests a new line of inquiry. If we relax the assumption that pressure must always be positive, can we build extremely compact, star-like objects that sit just outside their own Schwarzschild radius and still avoid forming a true horizon? To explore that question, theorists use an equation that describes the internal structure of relativistic stars, the Tolman-Oppenheimer-Volkoff equation. This relationship expresses the balance between the gradient of pressure, the distribution of energy density, and the curvature of space-time produced by that matter. In essence, it is the general relativistic version of hydrostatic equilibrium. It tells us how pressure must change with radius so that the inward pull of gravity is matched at every layer. If we feed into this equation an ordinary equation of state, where pressure increases with density and remains positive, we recover familiar neutron star solutions. The pressure is highest at the center, and falls smoothly toward the surface, where it drops to zero. The resulting objects occupy a region of mass and radius consistent with what we infer from observations of neutron stars in binary systems and pulsars. However, if we allow the possibility that pressure can become negative in some regions, the space of solutions changes character. Negative pressure is not something we encounter in everyday materials. But in general relativity, it is allowed in principle and contributes to space-time curvature in a different way from positive pressure. When we insert such an exotic equation of state into the TOV equation, the resulting profiles can behave oddly. Under many choices, the pressure either diverges to extremely large magnitudes or flips sign in ways that do not produce a stable configuration. Only for specific, finely tuned relationships between pressure and density do we find smooth solutions where the interior has negative pressure and positive energy density, matched to an exterior that looks, from the outside, just like the gravitational field of a compact mass. It is within this narrow band of possibilities that models like the gravastar appear. A gravastar, or gravitational vacuum star, is built from three main regions. At the center is an interior domain that behaves like a patch of de Sitter space, characterized by a constant positive energy density and an effective pressure that is negative and equal in magnitude to that density. Surrounding this interior is a thin shell of more conventional matter, and outside the shell the spacetime is the same as that around a non-rotating black hole with the same mass. In the de Sitter-like interior, the presence of vacuum energy and negative pressure leads to a delicate balance. The energy density tends to curve space-time inward, while the negative pressure contributes in the opposite sense in the gravitational field equations. Under the right conditions, these effects combine to produce a region that is spatially finite and static, rather than collapsing or expanding uncontrollably. The thin shell serves as a boundary, where the properties of the interior material are matched to those of the exterior vacuum. From far away, a gravastar would be hard to distinguish from a black hole. Light passing near it would follow nearly the same bending paths, and orbital motion around it would be similar. Its radius could lie extremely close to the Schwarzschild radius, only slightly larger than the size that would mark an event horizon if the object were a true black hole. For many purposes, it would behave as if it were one, at least in the limited sense captured by distant gravitational influence. Yet inside, according to the model, there is no singularity and no region from which escape is absolutely impossible. Instead of matter cascading inward beyond a horizon, there is a core dominated by vacuum energy, a kind of localized pocket of something very similar to dark energy. The object becomes a bridge between the physics of compact stars and the physics of the cosmic acceleration. This picture raises an intriguing possibility. In cosmology, dark energy is often modeled as a uniform vacuum energy permeating all of space, with a simple equation of state where pressure is negative and of the same magnitude as the energy density. This component is associated with the cosmological constant in Einstein's equations and provides a natural way to describe the observed accelerated expansion of the universe. In that global setting, vacuum energy acts everywhere at once, stretching the fabric of spacetime on the largest scales. Gravastars apply a similar equation of state, but in a localized, spherical region. We can think of each gravastar as a compact bubble of vacuum-like energy, confined and stabilized by its surrounding shell and by the geometry itself. Some researchers have explored scenarios in which a population of such objects could contribute to the overall dark energy budget, or at least mimic some of its effects when averaged over large volumes. The details of these models are subtle and still under study, but the conceptual link is clear. The same kind of energy that drives cosmic acceleration might also appear in concentrated form inside star-sized structures. This connection offers a new way of looking at extremes. Instead of treating black holes and dark energy as completely separate phenomena, one associated with the endpoints of stellar collapse, the other, with the future of the entire universe, we can see gravastars as hypothetical intermediaries that share features of both. They are as compact as black holes when viewed from outside, Yet their interiors are filled not with crushed ordinary matter, but with something closer to the uniform energy density that seems to shape the fate of cosmic expansion. Whether gravastars exist in nature is still an open question. The mathematics shows that such configurations are permitted within general relativity under certain assumptions about the equation of state. Observations of compact objects in X-ray binaries, gravitational wave events, and the environments of galactic centers are being examined for any small differences that could distinguish a true horizon from a very thin shell near the same radius. So far, the evidence is consistent with black holes, but the door is not entirely closed to more exotic alternatives. For our purposes, the important insight is that when gravity compresses matter close to the Buchdahl limit, and when we allow pressure to take on values beyond our usual experience, new categories of stars appear in the equations. These stars do not rely on nuclear fusion or on the degeneracy of electrons and neutrons. Instead, they lean on the properties of vacuum energy itself, on a form of pressure that pulls in a direction opposite to what we ordinarily expect. As we drift forward from here, this idea of localized vacuum energy will stay with us. It prepares us to look outward, beyond single stars, to the role that similar energy may play across the entire universe, and to the ways in which the same equations that describe the interior of an exotic object can also describe the large-scale evolution of cosmic space. Far from the familiar surfaces of stars, the geometry around a black hole leads us into shapes that seem to come in mirrored halves. When we follow the mathematics all the way out, the space of possibilities becomes wider than the single collapsing star that forms an astrophysical black hole, and the diagrams used to visualize space-time begin to show regions that look like reflections, extensions, and quiet side corridors of the same solution. To keep track of this, relativists often use Penrose diagrams, sketches in which the infinite reaches of space and time are compressed into a finite picture without destroying the causal structure. Light rays are drawn as straight lines at 45 degrees. Future lies upward, and entire universes can be represented on a single piece of paper. In such a diagram, a simple collapsing star that forms a black hole occupies only part of a larger pattern. The region outside the star and outside the horizon matches a portion of the ideal Schwarzschild solution, the solution that would exist if the black hole had been present forever rather than formed at some particular moment. When we stop insisting on a realistic collapse history and allow the ideal solution to stand on its own, the diagram extends. The familiar black hole region, the domain from which nothing can escape once it has crossed the event horizon, appears alongside another region that seems to be its time-reversed partner. There is also a second asymptotically flat exterior region, something like a separate universe connected to the first through the structure around the hole. In the full picture, the black hole is only one half of a cone-like shape in space-time, while the other half corresponds to a white hole that expels rather than swallows. The analogy often used is that of a geometrical cone. A cone has two sides, pointing in opposite directions, meeting at a tip. Yet, in everyday life, we usually handle only a single ice cream cone, cut away from the rest of the ideal shape. In a similar way, an astrophysical black hole formed from a collapsing star gives us only one side of a richer mathematical object. The other side does not appear in realistic collapse scenarios, but it is present in the full, eternally existing solution of Einstein's equations. Within that extended solution, a white hole is defined as a region of space-time from which particles and light can emerge, but into which they cannot enter. All possible paths that light could take either originate there or pass it by from the outside, always moving away. In contrast, in a black hole region, all such paths that cross the horizon are drawn inward, unable to turn back. The equations governing the geometry are the same, only the direction in which we trace the evolution changes. From the point of view of the field equations, a white hole is just as permissible as a black hole. Both satisfy the same underlying rules. Yet our universe shows clear evidence for objects that behave like black holes, while no convincing observation has yet pointed to a white hole. Theoretical work suggests that white hole regions embedded in a realistic environment would be unstable. decaying rapidly when any small amount of matter or radiation falls toward them. In that sense, they may be solutions that require idealized, finely tuned conditions that the real cosmos does not provide for very long. Still, the concept plays a role in shaping how we think about possibilities. It reminds us that once we accept the geometry of black holes, the extension to time-reversed counterparts and additional regions of space-time is not an arbitrary invention, but a quiet consequence of following the same equations into different corners of their solution space. When rotation is added, the picture acquires more structure. Real astrophysical black holes almost certainly spin, because the stars and gas that form them carry angular momentum. The solution that describes a rotating, uncharged black hole is called the Kerr solution. Its Penrose diagram is richer than the non-rotating Schwarzschild case. Instead of a single horizon and a central point-like singularity, there appear multiple horizons and a ring-shaped singularity, as well as interior regions where the behavior of spacetime becomes more intricate. Inside the outer event horizon of a Kerr black hole, there is an inner horizon, a surface beyond which the character of the radial coordinate changes again. In the classical solution, trajectories can thread their way through these interior domains, passing near the ring singularity in such a way that they avoid hitting it directly. Following the geodesics, the paths that free-falling particles and light would take, the mathematics allows routes that emerge into other regions of spacetime, effectively using the interior of the rotating black hole as a bridge. This is where the word wormhole often appears. A wormhole is a tunnel-like connection between separate regions of spacetime, a corridor that links two distant areas, or even two distinct universes. In the ideal Kerr geometry, the black hole interior acts as such a passage in the sense that there are paths which enter from one external region, traverse the interior, and exit into another. In simple diagrams, this can be drawn as two universes joined at the throat of the wormhole, with the ring singularity encircling the passage. However, the same analyses that highlight the existence of these paths also point to their fragility. Small perturbations, quantum effects, and realistic matter content are expected to destabilize the wormhole, causing the interior structure to collapse or be replaced by a different geometry before anything macroscopic could use it as a route. The idea remains mathematically clear and conceptually useful, but as far as we know, nature may not preserve these exact corridors in a way that permits travel. Even so, the presence of such features in the classical solution tells us something important. When general relativity is pushed to its extremes, it naturally generates scenarios that resemble familiar themes from speculative stories, passages between universes, mirror regions where events run in the opposite temporal direction, and networks of possible worlds, connected by shared origins. These themes do not need to be imported from outside. They are already present in the quiet language of the equations. Beyond individual black hole solutions, the notion of multiple universes also appears in broader cosmological contexts. There are models in which the universe undergoes repeated cycles of contraction and expansion, so that big bangs and big crunches succeed one another over immense timescales. In such scenarios, each cycle could, in principle, realize slightly different values of physical parameters, like the cosmological constant that measures vacuum energy. There are models in which space is much larger than the portion we can observe, with regions so distant that they never come into causal contact with us. Those regions may experience different symmetry-breaking patterns or low-energy physics, leading to a patchwork of domains with different effective laws. In quantum theory, ideas like the many-worlds interpretation describe each measurement-like interaction as giving rise to non-interacting branches of the quantum state, each branch containing a different outcome. If such a picture is taken literally at cosmological scales, it adds another layer of multiplicity, a vast collection of branches where microscopic choices and macroscopic histories diverge quietly and never meet again. In each of these frameworks, the word multiverse is used to describe the collection of all these domains, cycles, or branches. One motivation for introducing such a collection is to address the apparent fine-tuning of certain numbers in physics, particularly the small but positive value of the cosmological constant that seems to drive the accelerated expansion of the universe. Naively, many theories would predict vacuum energies much larger in magnitude. Yet observations point to a value that allows galaxies, stars, and, eventually, observers to form. Anthropic reasoning approaches this by noting that, in a multiverse where the cosmological constant can vary, most possible values would not permit long-lived structures. Regions with extremely large positive vacuum energy would expand too rapidly for matter to clump. Regions with large negative vacuum energy would recollapse quickly. Only in the relatively narrow band of values where expansion and structure formation can coexist would there be places for complex chemistry and, much later, beings capable of reflecting on the constants they measure. In that frame, our observed value is not surprising. It is simply typical among those regions compatible with our presence. This line of thought does not demand that we accept any particular multiverse model as a literal description of reality. It sits at the intersection of physics and philosophy, raising questions about testability and the meaning of probability when applied to an ensemble of universes. For some researchers, it is a useful way to organize ideas about the cosmological constant problem. For others, it feels unsatisfactory without clearer observational anchors. From the perspective of our quiet exploration, what matters is that the same mathematics which describes black holes, white holes, and wormholes also offers room for these wider ensembles. The landscape of solutions to our theories is richer than the single universe we directly observe. Some of those solutions resemble black holes that mirror themselves across a diagram. Others resemble networks of space-time patches, each with its own pattern of fields and constants. We move forward carrying these possibilities lightly. They remind us that the unseen structures suggested by our equations can take many forms, from compact stars filled with vacuum-like energy to large-scale collections of regions with different cosmic behaviors. Without needing to decide which of them the universe has chosen, we let them form a background of ideas as we turn, next, to the more focused question of dark energy itself, and the small but persistent pressure it appears to exert on the fabric of cosmic expansion. Far out on the largest scales, the universe behaves as if space itself carries a faint background energy, something that does not shine like stars or gather into galaxies, yet quietly guides how expansion unfolds over billions of years. The first strong hints of this came from a careful look at distant Type Ia supernovae in the late years of the 20th century. These stellar explosions are bright enough and similar enough to each other that they can serve as markers of distance across cosmological space. Teams of observers measured their brightness and their redshift, comparing how much the universe had stretched the light on its journey to us with how far away the sources seemed to be. If gravity from matter alone were in charge, expansion would slow over time as all the mass in the cosmos tugged inward. The data told a different story. The supernovae appeared dimmer than expected, as though they were farther away than a slowing universe would allow. The simplest way to account for this pattern was to accept that the expansion is speeding up. To describe such acceleration in the language of general relativity, cosmologists reintroduced an ingredient that had once seemed optional: the cosmological constant, usually denoted by the Greek letter lambda. In Einstein's equations, this constant acts like a uniform energy density that fills space with an unusual property. It does not dilute as the universe expands. Instead, each unit of volume carries the same small amount of energy, no matter how large the total volume becomes, and this energy contributes a negative effective pressure that tends to drive expansion rather than slow it. One way to picture this is to think of the vacuum not as empty, but as a medium with a tiny but persistent energy content. Quantum field theory suggests that even when no particles are present, fields fluctuate, and these fluctuations give rise to what is sometimes called zero-point energy. In simple models, if this energy is present uniformly everywhere, it behaves in gravity equations much like a cosmological constant. Dark energy, in this view, is nothing more exotic than the energy of the vacuum itself, acting with a steady push that becomes important only on the very largest scales. This neat identification brings with it a puzzle. When physicists try to estimate the vacuum energy using straightforward quantum calculations, adding up the contributions from various fields, the result is much larger than what is inferred from cosmological observations. The observed dark energy density is extremely small in ordinary units, just enough to influence expansion over billions of years. The naive theoretical estimates, by contrast, overshoot that value by a vast factor. Analogies are helpful here. It is as if a theory predicted that an average person should be as tall as the distance between Earth and the Sun, while in reality, people are a couple of meters tall. The mismatch is not a modest discrepancy that could be tuned away with a small adjustment. It suggests that something essential is missing in our understanding of how vacuum energy gravitates, or how different contributions might cancel. This tension between theoretical expectation and measured value is often referred to as the cosmological constant problem. Alongside this, there is a quieter timing puzzle, sometimes called the coincidence problem. Right now, in cosmic history, the density of dark energy and the effective density of matter are of the same order of magnitude. Earlier, when the universe was smaller and matter was more concentrated, matter dominated the dynamics. Much later, if expansion continues, dark energy will dominate overwhelmingly. We live in an era when the two are comparable, a relatively brief window on cosmological timescales. The question of why our observations happen to fall during this narrow interval is another strand in the broader discussion. Steven Weinberg proposed an approach that does not attempt to compute the cosmological constant from first principles, but instead considers a wider ensemble of possible universes in which lambda can take different values. In many of those hypothetical universes, expansion would be so rapid that matter could never cluster into galaxies. In others, a large negative cosmological constant could cause the universe to recollapse before complex structures formed. Only within a range of values where gravitational attraction and the repulsive effect of vacuum energy are balanced in a particular way can galaxies, stars, and planets emerge and endure. From that perspective, it is not surprising that observers find themselves in a universe where lambda lies within this narrow band. If dark energy were much larger in magnitude, either positive or negative, there would be no long-lived structures and no observers to ask about its value. Weinberg used this line of reasoning, sometimes called anthropic reasoning, to estimate an upper limit on the cosmological constant compatible with galaxy formation. Remarkably, the observed value turned out to be close to that limit. In this view, the question, why does the cosmological constant have this small positive value, is reframed. Instead of seeking a unique dynamical mechanism that forces lambda to a particular number, we imagine a broader landscape of possibilities in which different regions or universes realize different values. Observers arise only in a subset where the conditions allow complex structures, and we naturally measure a value drawn from that subset. It is a shift from seeking a single explanatory equation to accepting that selection effects might play a role in what we can observe. This idea connects quietly with the multiverse pictures associated with eternal inflation, with quantum branching, or with different low-energy vacua of a more fundamental theory. In all such scenarios, the constants of nature may vary from place to place, or branch to branch, and the cosmological constant is one of the quantities that can scan across a wide range. We do not need to commit to any specific multiverse model to appreciate the organizing role this framework can play. It allows us to see the measured value of dark energy not as an isolated accident, but as one outcome among many possibilities. At the same time, observations continue to refine how we describe dark energy itself. The simplest assumption, consistent with many measurements, is that it behaves exactly like a cosmological constant. Its energy density remains constant in time, and its equation of state parameter, relating pressure to energy density, is fixed at -1. Large-scale surveys of galaxies, quasars, and the cosmic web, along with improved supernova data and studies of the cosmic microwave background, have tested this model with increasing precision. Some recent analyses, including work from surveys such as DESI, have explored whether the data might be hinting at a small deviation from this simple picture. When cosmologists allow dark energy to have a time-varying equation of state and fit this more flexible model to the data, There are indications still under evaluation that a slowly changing dark energy component could be compatible or even slightly favored. If that pattern holds up, as more data are collected and systematic effects are better understood, it would suggest that dark energy is not exactly a cosmological constant, but perhaps the manifestation of a dynamic field or a more complex structure. In that broader space of possibilities, models where vacuum-like energy appears both in local structures and in the cosmic background gain renewed interest. Gravastars, for example, concentrate vacuum energy inside compact objects, while other theories describe rolling scalar fields that change slowly over time, known under names like quintessence. All of these share the idea that what we call dark energy may have internal dynamics or microstructure that we do not yet fully see, and that the apparent constancy of lambda might be only an approximation valid over a limited era. For our quiet journey, the key point is that dark energy remains one of the most open topics in contemporary cosmology. We are confident that something with the gravitational behavior of a small, positive energy density pervading space is present because its influence shows up in multiple, independent lines of evidence. We are less certain about its origin, its exact nature, and whether it is truly unchanging. Theoretical work ranges from attempts to calculate vacuum energy more accurately to explorations of modified gravity and dynamic fields. Observational programs continue to map the expansion history and the growth of structure with ever finer detail. As we drift onward through this landscape of ideas, we carry with us a picture of a universe whose large-scale behavior is shaped by an almost imperceptible background component. It does not glow. It does not clump in the way matter does. And yet it participates in the same gravitational framework that describes stars, black holes, and gravastars. Somewhere between the equations that predict vast energies and the measurements that reveal a far smaller value, there is a story still unfolding, one in which the fabric of space itself plays a quiet, persistent role in how the cosmos evolves over time. Around every large galaxy, including our own Milky Way, there seems to be a wide and invisible halo that extends far beyond the bright disk of stars. We do not see this halo directly, yet its presence is written into the way stars and gas move, into the paths traced by light from more distant galaxies, and into the pattern of structure that has grown slowly out of the early universe. When astronomers measure how fast stars orbit in a spiral galaxy, they find that the outer stars move much more quickly than they would if only the visible matter were present. If we added up all the starlight and gas and used that as our estimate of the total mass, those outer stars would be moving so fast that they should drift away over cosmic time. Instead, they remain bound. The most straightforward explanation is that there is additional mass, spread out in an extended halo, contributing gravity without shining. A similar story unfolds on larger scales. In galaxy clusters, the speeds of galaxies orbiting the cluster center point toward a mass far in excess of what is seen in stars and hot gas. Light from even more distant galaxies is bent and distorted as it passes through these clusters, an effect known as gravitational lensing. The pattern of that distortion reveals the shape and extent of an unseen mass distribution that wraps around and between the luminous components. On the largest scales, the way galaxies and clusters arrange themselves into filaments and walls over billions of years fits simulations only when an extra, invisible matter component is included. Taken together, these lines of evidence support the idea that the cosmos contains a dark matter component, a form of matter that interacts very weakly with light and ordinary particles, yet participates fully in gravity. In modern cosmological models, this component is not an optional detail. It is woven into the history of structure formation, from the first small clumps in the early universe to the vast web of today. Once we accept that such a component exists, the question of its nature becomes one of the central puzzles of contemporary physics. For a long time, one of the leading ideas was that dark matter consists of new elementary particles beyond the known ones in the Standard Model. These hypothetical particles, often called WIMPs in earlier literature, were thought to be massive and to interact very weakly with ordinary matter. Other candidates included axions, ultralight fields, or heavier neutrino-like particles. Each proposal came with its own characteristic mass range and interaction strength, and each suggested particular ways in which the particles might occasionally scatter off nuclei or produce subtle signals. Laboratories on and beneath Earth, experiments buried under mountains or deep in ice, and detectors placed in orbit have been built to look for these faint interactions. They watch for rare flashes in crystals when a dark matter particle might collide with an atomic nucleus, for tiny changes in resonant cavities that could hint at axions, or for irregularities in cosmic ray backgrounds and gamma ray emissions. Over the years, these experiments have explored many of the simplest, most natural regions of parameter space. The combinations of mass and interaction strength that seemed especially plausible at the outset. So far, no clear, widely accepted detection has emerged. Each new generation of experiments has pushed the limits further, ruling out broad ranges of possibilities. The absence of a signal does not mean that dark matter is not made of particles, but it does suggest that if particle dark matter is real, it may be lighter, heavier, or more weakly interacting than initially expected. This persistent silence in the laboratory has encouraged many researchers to look back at alternatives that rely more directly on gravity itself. One such alternative is that a significant part, or even all, of dark matter might be composed of compact objects. Black holes formed not from stars, but from density fluctuations in the very early universe. These are known as primordial black holes. Unlike stellar black holes, which are the remnants of massive stars that exhausted their fuel and collapsed, primordial black holes would have formed long before the first stars, when the universe was still hot, dense, and rapidly expanding. In that early epoch, tiny variations in density were imprinted in the plasma, seeds that would later grow into galaxies and clusters. If some of those variations were much larger than average, local regions could have become dense enough to collapse directly under their own gravity, forming black holes without passing through any stellar phase. The masses of these objects would depend on the conditions at the time of their formation and could span a wide spectrum, from much less than the mass of an asteroid up to many times the mass of the Sunday. This idea is appealing because it does not require new fundamental particles beyond those already used in general relativity and standard cosmology. The same framework that describes the overall expansion of the universe and the growth of structure also permits direct collapse in regions where the density briefly exceeds a critical threshold. Primordial black holes, if they exist in sufficient numbers, would behave gravitationally like any other dark matter, forming halos, influencing galaxy rotation, and contributing to lensing. They would simply be concentrated packages of mass scattered through space. However, compact objects are not invisible in every context. A black hole passing in front of a distant star can act as a tiny lens, magnifying the star's light for a short time as their alignment changes. Surveys that monitor millions of stars in the Milky Way and in nearby galaxies look for such microlensing events. The frequency and characteristics of those events place limits on how many compact objects of a given mass can be present in the galactic halo. Similar constraints arise from the way primordial black holes would affect the cosmic microwave background or disrupt stellar systems and wide binaries. Over time, these observational efforts have excluded primordial black holes as the dominant form of dark matter over many mass ranges. Black holes, much more massive than the Sun, in particular, are strongly constrained by various astrophysical effects. Intermediate mass ranges are limited by microlensing and dynamical arguments. What remains especially interesting is a window at much smaller masses, around 10 to the 17th to 10 to the 23rd grams, comparable to asteroids. In this range, current methods have a harder time placing tight bounds, and there is still room, in principle, for primordial black holes to make up a large fraction of dark matter. We can think of the search as a gradual process of checking pockets where dark matter might be hiding. Many of the obvious ones, new particles with certain interaction strengths. Black holes in certain mass bands have been turned inside out with no definitive result. The asteroid mass window for primordial black holes is one of the places that has not yet been thoroughly examined, not because it is protected by any deep principle, but because it is technically challenging to probe. If black holes in this mass range were drifting through the Milky Way halo, some of them would, from time to time, pass through the solar system. Individually, each would carry only a small mass compared to the Sun or the planets, but their gravitational fields would still tug very slightly on anything nearby. Over many years, such a passage would imprint a tiny, smooth deviation in the orbits of planets and spacecraft. The effect would be far too small to notice with casual skywatching, yet it would be present in the detailed record of positions and timings that astronomers keep. In that sense, the solar system itself becomes a kind of detector. The orbits of Earth and Mars, the timing of signals sent to and from spacecraft, and the careful reconstruction of ephemerides, tables of predicted planetary positions, collectively encode a history of how mass is distributed nearby. If a primordial black hole of the right mass slipped through, the subtle disturbance it caused could, in principle, be teased out of the data by comparing extremely precise observations with the expectations from models that include only known bodies and forces. In the background, the more traditional signals of dark matter remain: the flat rotation curves of galaxies, the lensing maps of clusters, the ripples in the cosmic microwave background. They continue to point toward an unseen mass component that outweighs ordinary matter by a factor of several. What changes as we move through these ideas is not that evidence, but our list of candidates and the ways in which we imagine listening for them. We are left, for now, with a picture in which dark matter might be a new kind of particle, too shy to reveal itself in present-day detectors, or a population of compact objects like primordial black holes, scattered quietly through galactic halos and occasionally wandering through planetary systems. In both cases, the clues arrive as slight deviations in motion and light, and in the long record of how gravity has guided the structures around us. Out in the Milky Way's halo, the solar system is just a small clearing in a much larger landscape, a place where luminous planets and dust move inside a background of unseen mass. If dark matter were made of primordial black holes, then that background would not be a smooth fog of particles, but a slow drift of compact, invisible objects passing in long arcs around the galactic center. From time to time, one of them would thread its way through the region where the sun and planets move. We can picture these primordial black holes as tiny in size but heavy in mass, like marbles made of concentrated gravity. For the mass range that is still allowed by current observations, from around 10 to the 17th up to 10 to the 23rd grams, each one would be smaller than an asteroid, yet far denser than anything made of rock or ice. If they supplied all of the dark matter near the solar system, estimates suggest that the low mass end of this range would correspond to a large number of these objects per unit volume, enough that there would almost always be at least one within the region traced by the orbits of the inner planets. At the higher mass end, they would be rarer but still present, with individual black holes passing through the broader solar system every few decades to every few centuries. These numbers show that if primordial black holes in this mass window do make up dark matter, they would not be strangers to our local neighborhood. They would be part of the same invisible component that shapes the Milky Way's rotation. The question is not whether they would ever come near, but what kind of imprint they might leave, and whether that imprint could be detected amid all the other motions in the system. The gravitational influence of a single passing black hole on a planet like Mars is modest. Consider an object with a mass around 10 to the 21st grams, moving on a wide, almost straight path through the outer region of the inner solar system. As it glides past, its gravity tugs very slightly on Mars, altering the planet's velocity by a minute amount. At the moment of closest approach, the change is so small that it would be imperceptible to any casual measurement. Mars continues along a path that looks, to the eye, almost identical to the one it would have followed without the encounter. The key is that orbits are cumulative. A tiny change in velocity, once introduced, does not disappear. It shifts the path by a very small amount, and over time that shift grows. A familiar analogy is a car on a long, straight highway whose cruise control is set slightly differently from what we intended. The difference of 1/100 of a kilometer per hour is too small to notice in the first minute, But after many hours, the car will be noticeably ahead or behind where we might have expected it to be. For Mars, a minute change in orbital speed or direction introduced during a brief encounter with a primordial black hole would, over the course of years, grow into a positional offset. Calculations suggest that for certain masses and encounter distances, the displacement after about a decade could reach the scale of a meter compared to the orbit predicted by a model that does not include the passing object. A meter is very small against the size of an orbit, measured in hundreds of millions of kilometers. Yet it is not beyond the reach of modern tracking techniques. This is where the idea of using the entire solar system as a detector comes into focus. If we can predict the motion of planets to high precision and compare those predictions to decades of precise measurements, any systematic, unexplained deviations might hint at the passage of something unseen. The system becomes a kind of gravitational observatory, not by adding new instruments, but by reading the fine structure of orbits that we already monitor. For Mars in particular, our knowledge of its path has improved dramatically over the last few decades. Planetary ephemerides, such as those produced and updated by space agencies, combine a wide variety of data: radar ranging to planets, optical observations from ground-based telescopes, spacecraft navigation records, and signals sent to and from orbiters and landers. Each time a radio signal is transmitted from Earth to a spacecraft circling Mars and back again, the timing of that round trip encodes the distance to extraordinary accuracy. Over years, thousands of such measurements accumulate, tracing the changing geometry between Earth, Mars, and the Sun in detail. These data are not just a list of positions. They feed into dynamical models that include the gravitational pull of the Sun, planets, moons, and major asteroids, as well as corrections for relativistic effects and non-gravitational forces acting on spacecraft. The result is a set of ephemerides that can predict where Mars will be at a given time, with uncertainties that can be on the order of meters, or even smaller, in certain directions. That level of precision is essential if we want to be sensitive to the subtle, delayed signatures of a passing compact object. The solar system, in this view, is an ongoing experiment. Each new mission to Mars, each additional year of tracking data, refines our picture of how Mars moves. If a primordial black hole were to pass nearby, its influence would be embedded in that record. Hidden among the normal signals from known bodies and forces, there would be a small, coherent deviation that does not match any combination of recognized perturbations. The analysis challenge is to separate such a signal from the many other effects that can introduce shifts at the meter level. One of those potential sources of confusion is the population of asteroids. Large asteroids can also tug on planets and spacecraft. Many have masses comparable to what a primordial black hole in the allowed range might have, and their orbits lead them through regions where they can exert measurable gravitational influence. If we did not know about these asteroids, or if their masses and trajectories were poorly constrained, their effects could masquerade as those of an unseen compact object. Fortunately, the larger asteroids, those with sizes of tens to hundreds of kilometers, have been catalogued with considerable completeness. Their positions, orbits, and, in many cases, masses are known well enough that their contributions can be modeled. They also share common patterns. They tend to lie near the plane of the solar system, in belts and families, with orbital speeds and orientations shaped by the long history of planetary formation. Their interactions with planets repeat in predictable ways, as orbits bring them into similar configurations again and again. A primordial black hole passing through the system would differ in several respects. It would not be bound to the Sun in the usual sense, but would follow a trajectory inherited from its motion through the galactic halo. That trajectory might slice through the solar system at a steep angle to the ecliptic, arriving from directions where few asteroids travel. Its speed relative to the Sun would likely be set by the typical velocities in the halo, which are higher than the orbital speeds of planets and most main-belt asteroids. The resulting gravitational perturbation on a planet would be a smooth, one-time event, with a characteristic shape in time that does not recur periodically. By studying the detailed form of any anomalous orbital deviations, how they build up and then settle, from which direction they appear to come, and how they correlate across different planets or spacecraft, we could, in principle, distinguish between a passing halo object and the accumulated influence of known small bodies. Statistical analysis over many years and many potential events would further refine this separation, highlighting patterns that match the expected signature of transient, high-speed perturbers. All of this remains a developing idea rather than an established detection method. It rests on the continued improvement of ephemerides, on careful modeling of all known influences, and on the assumption that any primordial black holes in the relevant mass range pass through often enough to leave a detectable mark over human timescales. Yet the concept itself is striking in its simplicity. Without building a new telescope or a new underground detector, we can turn our attention to the orbits we already track and ask whether they carry traces of something small, compact, and dark moving through the system. As our measurements of the solar system grow more precise and our models more detailed, the space of possibilities narrows. If no unexplained deviations appear, the idea that primordial black holes make up all of dark matter in the asteroid mass range will be constrained further. If subtle, coherent anomalies are found and survive all other explanations, they could point toward a population of invisible objects passing quietly between the planets, linking the story of galactic halos to the slow, steady motion of Mars around the Sunday. For more than 20 years, Mars has been accompanied by a small fleet of silent machines, circling above its surface or resting on its dust, sending a steady stream of signals back toward Earth. Each radio pulse that leaves an antenna, crosses interplanetary space, bounces from a spacecraft and returns, carries a precise measure of distance and time. Placed together, these signals form something like a long recording of how Mars moves, a continuous trace of its orbit, written in delays measured down to tiny fractions of a second. We can picture this record as a line of notes on a very extended score. Every tracking session, every ranging experiment, adds another mark, another point on the curve that represents the distance between Earth and Mars at a particular moment. Over years, the pattern of those distances reflects the geometry of the two planets as they circle the Sun, sometimes closer, sometimes farther apart, in a slow, repeating dance. If nothing unexpected ever tugged on them, the pattern would be almost perfectly predictable from the known masses and positions of the major bodies. In that sense, the ephemeris of the solar system is like an archive of motions. It is not just a snapshot, but a layered history. Within this history, a passing primordial black hole would not produce a sharp, dramatic event. Instead, it would introduce a slight, smooth deviation that begins at some time, grows gradually as orbits respond, and then persists as a small offset in position and velocity. The goal is to read that deviation in the same way that one might notice a single instrument playing slightly off the expected pitch in a long orchestral performance. To make this search concrete, researchers turn to simulations. They take a model of the solar system that already includes the Sun, the planets, major moons, and a large collection of asteroids. And they allow this system to evolve under gravity in a computer. This is often called an N-body simulation, where N is the number of objects whose mutual attractions are being tracked. Into this virtual solar system, they insert a notional primordial black hole with a particular mass and trajectory, letting it drift through the region of interest. The result of each such run is a set of slightly altered orbits. Mars, Earth, and other bodies shift by tiny amounts compared to the version of the simulation without the black hole. By repeating this process for many different masses, paths, and timings, it is possible to build up a library of patterns, a collection of examples showing how the long-term ephemeris would look under various hypothetical encounters. Each pattern is like a word in a dictionary, describing one possible way the system could respond to a passing compact object. With this dictionary in hand, the recorded data from actual tracking can be compared to the simulated traces. Statistical techniques can be used to ask whether the real ephemeris resembles any of the patterns associated with a primordial black hole passage more than it resembles patterns produced by other, more mundane sources of deviation. The comparison does not rely on a single event, but on the overall shape of the residuals, the small differences between observed positions and those predicted by a model that excludes the hypothetical black hole. The difficulty is that the solar system is not an empty laboratory. Many other influences can introduce small discrepancies. Asteroids are a major example. Each sizable asteroid exerts a gravitational pull on planets and spacecraft. And while a single asteroid may have only a modest effect, the cumulative influence of thousands can matter. As surveys discover new objects and refine their orbits, ephemeris models are updated to include them. Before that happens, their unmodeled pull can appear as a faint, slowly changing disturbance in planetary motion. Beyond asteroids, there are subtler factors. Tidal effects from the distribution of mass within planets and moons, slight uncertainties in planetary masses themselves, small non-gravitational forces on spacecraft from sunlight or thermal radiation, and even minute drifts in the timing systems used to measure signal travel times can all contribute. Each of these has its own characteristic signature, and careful modeling is needed to take them into account. The better these influences are understood, the more clearly any leftover pattern can be examined. Listening for a primordial black hole in this environment is a bit like trying to recognize a quiet voice in a public space where many conversations are happening at once. To hear that distant voice, it helps to know in advance the timbre and rhythm of closer voices so that they can be subtracted, or at least recognized and set aside. In the same way, modeling known sources of noise, asteroids, tides, instrument behavior allows the remaining signal to be inspected for features that line up with the templates from simulations. There is also the question of how to define convincing evidence. A single, modest deviation that could be attributed to an unmodeled asteroid or a small systematic error is not enough. Researchers look for patterns that are coherent over time and across different types of measurements, and that have shapes consistent with an external perturber moving on a high speed, nearly straight path through the system. They also consider how likely it is that an ensemble of known effects, added together, could mimic such a pattern by chance. Two complementary paths emerge from this approach. One is retrospective, by taking the ephemeris data already collected over past decades, especially those involving Mars and other well-tracked bodies, and comparing them to the library of simulated patterns. It may be possible to uncover a historical event that fits the profile of a primordial black hole encounter. In that case, the passage would already have happened, and its echo would be embedded in the differences between observed and predicted positions. The task is to recognize that echo and to show that no combination of known influences can reproduce it as naturally. The other path looks forward. As tracking continues and new missions refine our knowledge of planetary orbits, analysts can monitor the emerging data in near real time. If a new, coherent deviation begins to appear, growing slowly in a way that matches one of the template patterns, that deviation can be flagged for closer study. Observatories can then check whether any bright object, such as an uncharted asteroid, is moving along a path that could account for the effect. If no luminous candidate is found, and the pattern continues to match what would be expected from an unseen compact object passing through, the case for a primordial black hole candidate would become stronger. Neither path guarantees a discovery. It may be that primordial black holes do not make up dark matter, or that they are present but rare enough that none has passed close enough to leave a measurable signature within the span of our current records. Even so, the process of searching brings a certain clarity. It sharpens models of the solar system, improves catalogues of asteroids, and tests the limits of how well we understand the interplay of gravity and motion in our own neighborhood. As we drift onward through this exploration of the unseen, the idea that the solar system itself can serve as a detector adds another layer to the way we imagine listening to the universe. Nearby, within a few astronomical units of the Sun, the quiet arcs of planets and spacecraft carry information about any small, compact masses that may have wandered through. Far away, across the Milky Way halo and beyond, the rotation of galaxies, the lensing of distant light, and the pattern of cosmic structure continue to trace the broader presence of dark matter. Between these scales, a possible population of primordial black holes links the large and the local, offering one more way in which the invisible universe might leave a trace in the motions we have been watching for so long. By now, we have gathered a small constellation of ideas that live more in equations than in telescopes. Stars, made mostly of vacuum, time-reversed black holes, and entire collections of universes with different properties. They sit near the edge of what current observations can test, close enough to be taken seriously, distant enough that we still speak about them with care. Gravastars are a good example of this in-between status. From far away, a gravastar would look almost indistinguishable from a black hole with the same mass. Its external gravitational field would match the familiar Schwarzschild or Kerr solution. Light passing close by would bend in nearly the same way. Orbits of nearby stars and gas would follow the same paths. In terms of the geometry outside, the two objects share the same outline. The proposed difference lies inside. Instead of matter collapsing all the way past a horizon and toward a singularity, a gravastar contains an interior region filled with something that behaves like vacuum energy, with positive energy density and negative pressure, matched to a thin shell of ordinary or exotic matter, and then to the usual exterior solution. In that picture, there is no event horizon and no point of infinite density, only a very compact configuration of spacetime supported by the properties of vacuum-like energy. From a distance, it is hard to see how this difference could be detected. One of the most promising ideas involves gravitational waves. When two very compact objects spiral toward each other and merge, the final stages of their coalescence produce a characteristic ring-down signal. As the merged object settles into a stable state. For ordinary black holes, this ring-down can be described by a set of oscillation modes, determined only by the mass and spin of the final hole. For gravastars, the absence of a true horizon and the presence of a reflective inner structure could, in principle, modify the way these oscillations fade, producing faint echoes or small shifts in the spectrum of frequencies. Detectors such as LIGO, Virgo, and CAGRA have already observed many mergers between compact objects, most of which are interpreted as black hole pairs or neutron-star pairs. Analysts have searched some of these signals for hints of the subtle features that gravastar models predict. So far, no clear, widely agreed departure from the black hole description has emerged. Within the limits of current sensitivity, the simplest interpretation remains that the observed mergers involve ordinary black holes as described by general relativity. That does not rule out gravastars. It means only that, for now, the data do not require them. The idea stays in a kind of quiet limbo, mathematically consistent, conceptually suggestive, and still waiting for a decisive observational signature. As gravitational wave detectors improve and accumulate more events, the space of allowed alternatives will shrink. Gravastars may eventually be pushed into a narrower corner of parameter space, or a future signal might show a pattern that fits them better than any black hole model. At the moment, the community leans toward black holes as the minimal explanation, while keeping the door open to more exotic possibilities if evidence appears. White holes occupy an even more unusual position. In the idealized extension of the Schwarzschild solution, they arise naturally as the time reverse of black holes, regions from which matter and light can emerge, but into which nothing can enter. In the real universe, with stars that collapse at finite times and environments filled with background radiation, these regions seem difficult to realize. Small perturbations falling toward them would disrupt their structure, and no convincing astrophysical examples have been identified. Recently, however, some approaches to quantum gravity have revisited the concept in a new context. In semi-classical pictures, black holes radiate slowly via Hawking radiation, losing mass over extremely long times. As they shrink, their temperature rises and the evaporation accelerates. But the final stages of this process, when the black hole approaches very small mass and very high curvature, are beyond the reach of these approximate methods. Different quantum gravity frameworks propose different resolutions. In some loop-inspired models, the collapsing interior does not end in a singularity. Instead, the strong curvature triggers a transition, a kind of tunneling in the space of geometries, in which the black hole interior connects to a new region that behaves like a white hole. In this scenario, information that had fallen into the black hole is not destroyed. It is stored and then released very slowly through the white hole phase, spread over long timescales. The full life cycle becomes formation from collapse, a long period of gradual evaporation, and then a final transformation into a small white hole that leaks what remains. This story offers a way to address the information puzzle associated with black holes without abandoning the basic structure of general relativity. It respects the idea that fundamental evolution is unitary while changing the internal picture of what happens at extreme density. Yet at present it remains a theoretical construction. The timescales involved for astrophysical black holes are vastly longer than the age of the universe, and even for smaller holes, any observable signal from such a transition would be faint and distant in time. As with gravastars, the idea is part of a landscape of possible resolutions, waiting for a clue that could distinguish it from competing narratives. Beyond individual objects, there is the broader question of multiverses. When we looked at dark energy and the cosmological constant, we encountered the difficulty of explaining why the vacuum energy appears to take such a small, positive value, large enough to influence cosmic expansion, small enough to allow galaxies and stars to form. One family of proposals frames this not as a single number prediction, but as a selection effect. In those proposals, the fundamental theory permits many different regions or branches, each with its own effective value of the cosmological constant and possibly other parameters. Some regions expand too quickly for any structure to condense. Others recollapse almost immediately. Only in a relatively narrow band of values do long-lived galaxies and planets emerge. Observers can arise only in those regions, and so it is not surprising that measurements carried out by such observers find themselves within that band. The smallness of the cosmological constant is then not derived from a unique dynamical mechanism. It is contextualized by the requirement that the environment be compatible with complexity. Various versions of multiverse ideas exist. Cyclic cosmologies imagine repeated expansions and contractions, each cycle potentially sampling different conditions. Eternal inflation pictures a space-time in which inflationary regions continue to form, each with different vacuum energies and low-energy physics, producing a mosaic of pocket universes. Quantum many-worlds interpretations consider branching structures in the global wave function, with different outcomes realized in non-communicating branches. In each case, there is a larger structure in which our observed universe is only one part. These constructions are conceptually rich but difficult to test. At present, there is no widely accepted way to probe other regions or branches directly, nor to measure the distribution of cosmological constants across them. For some physicists, the multiverse framework is attractive because it turns fine-tuning into a statistical question. Among all the allowed possibilities, a small subset allows observers, and we should expect to find ourselves in that subset. For others, this feels incomplete, because it postpones the search for a concrete mechanism that sets the parameters, and because it relies on ensembles that may never be directly accessible. Both attitudes coexist. Some researchers treat multiverse reasoning as a useful working tool, a way to organize and compare theories that predict broad landscapes of vacua. Others view it as a sign that our current understanding is provisional and that a more predictive framework remains to be found. In either case, the idea serves as a reminder that our observed universe might not exhaust what the underlying laws make possible, even if what lies beyond remains out of reach. Standing among these possibilities, gravastars that imitate black holes, white holes that might emerge from quantum processes, and multiverses that extend the notion of a cosmos beyond a single connected region, we find ourselves in a familiar position. The mathematics permits more structures than observations have yet confirmed. Experiments and surveys slowly increase their reach, looking for small departures from the simplest models. Along the way, the space of viable theories narrows, but it rarely collapses to a single line. It may be that some of these ideas will, in time, join black holes and dark matter as accepted parts of the cosmic inventory. It may be that they will instead be replaced by different constructions that fit new data more naturally. For now, they remain part of the quiet backdrop to our understanding. Shapes traced in diagrams, scenarios explored in simulations, and conceptual tools that help us think about what the universe could be, even as we continue to watch the limited region we can see. If we look backward through the history of astronomy and physics, a recurring pattern starts to appear. Neptune entered our maps of the solar system before anyone had actually seen it through a lens. The orbit of Uranus showed a tiny but persistent discrepancy from what Newtonian gravity would suggest if only the known planets were present. Rather than discard the theory, some astronomers asked what would happen if there were an unseen planet tugging from farther out. When telescopes were pointed to the right part of the sky, that invisible perturbation resolved into a new world. Antimatter followed a similar path in a different domain. When Paul Dirac wrote down an equation to describe the electron, the mathematics implied the existence of solutions with opposite charge and mirrored properties. At first, these solutions seemed abstract, possibly a sign that the equation was being pushed beyond its proper range. Later, particles matching those predicted properties were found in cosmic rays and in laboratory experiments. The extra pieces of the equation were not artifacts. They were a real part of the particle inventory. The cosmic microwave background, the faint radio glow that fills all of space, was also anticipated. Theories of a hot, dense early universe suggested that once matter and radiation decoupled, a relic bath of photons should remain, cooled by expansion into microwave frequencies and arriving from every direction with almost the same intensity. When radio engineers later encountered an unexpected background hiss in their instruments, the match to the predicted properties of that relic light became clear. Even black holes, which now occupy such a central place in astrophysics, spent many decades as largely theoretical objects. Calculations in Newtonian gravity hinted that sufficiently compact stars could trap light. General relativity made the concept more precise, revealing event horizons and the possibility of regions from which no signal can escape. For a long time, these were seen more as curiosities or even warnings about the limits of the theory. Only when observations of sources like Cygnus X1 and the orbits of stars around galactic centers stacked up did the community begin to treat black holes as commonplace constituents of the universe. The same pattern runs through all of these stories. It begins with a discrepancy in motion, a small irregularity in spectra, a background noise that does not quite match expectations. A theoretical framework is then extended or adjusted to account for the anomaly, often by proposing a new entity or mechanism. Years or decades later, when instruments improve and more data accumulate, observations resolve the earlier ambiguity, either confirming the new entity or pushing the theory in a different direction. Theory walks a little ahead, observation eventually catches up, and together they shift our sense of what is real. Gravastars, white holes, dark energy, and primordial black holes occupy a similar stage. They are natural possibilities within the structures of our current theories, grounded in the same equations that have already succeeded elsewhere. At the same time, they have not yet been singled out by any observation that demands them. They may follow the path of Neptune and the cosmic microwave background, moving from the realm of hints into that of clear detection. Or they may serve as stepping stones toward future ideas that will describe new data more precisely. For now, they remain in that characteristic middle space where the universe has offered clues, but not yet a full answer. When we look at how we hear those clues, two complementary modes stand out. One ear listens in the world of equations. It hears the Einstein field equations balancing curvature with energy and pressure. The TOV equation describing how pressure gradients support compact stars, the cosmological constant, sitting as a simple term that changes the large-scale behavior of expansion. It traces geodesics in Penrose diagrams, examines stability conditions for vacuum-filled interiors, and explores how different choices of equation of state give rise to different structures. The other ear listens in data. It follows the arcs of planets in ephemerides, the way radar signals bounce back from spacecraft around Mars and Saturn, and the arrival times of pulses from distant pulsars. It pays attention to how galaxies rotate and how clusters bend the light behind them. It monitors the tiny stretching and squeezing of space in gravitational wave detectors as compact objects merge in distant galaxies. It traces the pattern of galaxy clustering and the way the expansion rate changes with redshift in surveys designed to probe dark energy. Both modes are tuned to the same universe. The abstract ear hears what is mathematically allowed, mapping the space of possible behaviors under known laws. The observational ear hears what actually happens in the specific region of spacetime we inhabit. Where the two modes overlap, confidence grows. Where they diverge, questions multiply and new work begins. Exotic hypotheses about stars dominated by vacuum energy or tiny black holes drifting through the solar system are not free-floating speculations. They are anchored at one end in rigorous equations and at the other in measurements that are already in hand or soon to arrive. Looking ahead, the ways in which we listen are likely to become more sensitive. Ground-based gravitational wave detectors are being upgraded, and future facilities will extend their reach to fainter and more distant events. A space-based observatory such as LISA is planned to listen at lower frequencies, where massive black hole binaries and perhaps other structures sing. In those signals, small deviations in the late-time ringing of mergers could reveal whether the final object has a true horizon or a more complex surface. On cosmological scales, surveys like DESI and others map the three-dimensional distribution of galaxies and quasars, tracing the subtle imprint of dark energy on the pattern of structure and on the expansion history. As the precision of these maps improves, models where dark energy evolves over time or interacts with other components can be tested, and hints of behavior beyond a simple cosmological constant may emerge or be ruled out. Closer to home, continued missions to Mars, the Moon and other bodies refine planetary ephemerides. Each additional lander and orbiter adds more points to the long recording of orbital motion. Future missions may include even more precise timing and ranging systems, turning the solar system into a progressively sharper probe for small gravitational disturbances. If primordial black holes do pass through, the record of their influence will be written into the residuals between observation and prediction. All of these projects share a common aim: to reduce uncertainty about the universe by improving the clarity with which we hear its quiet signals. They do not force particular outcomes. They simply move the boundary between what is accessible and what remains out of reach, allowing some possibilities to fade and others to come into focus. Within this unfolding work, our own position is modest and steady. We are observers who can allow different hypotheses to coexist in our awareness without needing to choose a definitive winner tonight. Dark matter may turn out to be a new kind of particle, or a population of primordial black holes, or something else not yet fully imagined. Dark energy may be a true cosmological constant, a slowly changing field, or an emergent phenomenon tied to space-time in a way we do not yet understand. Gravastars, white holes and multiverses may move toward or away from the center of scientific attention as evidence accumulates. It is enough for now to acknowledge that the present universe holds more open questions than firm answers at these extremes. The lack of closure is not a flaw in the enterprise. It is a natural feature of inquiry at the boundary of knowledge. Each unresolved thread marks a place where theory and observation have not yet fully met, where the pattern of history suggests that new understanding may eventually appear. As we remain here, somewhere between equations and orbits, we share the stance of a quiet witness. We watch the way planets trace repeatable paths around the sun, knowing that in those paths, there may be tiny deviations left by things we have not yet named. We consider the shapes drawn by our mathematics and the structures they permit, knowing that only some will find counterparts in the sky. The universe continues to offer hints through small anomalies and persistent regularities, and our various instruments, both conceptual and physical, continue to refine what we can hear. In that ongoing exchange, the unseen components we have followed in this journey keep their character. Exotic stars, gravastars, white holes, dark energy, and primordial black holes remain, for the moment, as quiet possibilities. They are present as slight distortions in the way space expands, in how orbits shift, in how waves in space-time fade after a collision. They are not yet vivid pictures on a screen, but they trace their outlines in the long, patient records we collect. While that continues, the broader story does not need a final sentence. The universe carries on evolving. Our instruments carry on listening, and the space between theory and observation carries on narrowing and opening in different places. Somewhere within that process, the things we cannot yet see keep whispering in the language of motion and curvature, and we, in our own time, keep learning how to listen. By the time we reach the end of this journey, black holes begin to look different. They are no longer only violent endpoints of massive stars, but natural elements within a much larger, largely invisible cosmic landscape. Compared with dark matter, dark energy, or possibilities such as primordial black holes wandering through space, the black holes we thought we understood seem almost familiar. The solar system no longer appears as an empty island, but as a region, moving through a background shaped by unseen masses, which may include small black holes passing silently nearby, leaving no obvious mark beyond the most delicate shifts in orbital motion. It is this quietness that makes the search slow, patient, and deeply challenging. Thank you for staying with us to the end, for choosing to listen to subtle details rather than waiting for dramatic spectacle. The universe still holds many surprises and unnamed mysteries, not only in distant galaxies, but within the space we thought was already known. We will continue exploring together, where simple questions can open unexpected depths in the vastness of the cosmos.